So normal helium, the nucleus doesn't talk, the electrons don't talk. If I do helium-3, the nucleus will talk, but what about the electrons? Still they don't talk. And therefore, you can actually see, you can do two different things on the system by simply applying magnetic field. You can look for either the proton spin or the nucleus spin, or you can look for the electron spin if the electron has a net spin angular momentum in the situation. So if I take hydrogen for example, yes, I can do it because I have S equals 1/2. Apply a magnetic field, it must split as plus half and minus half, excepting that the order of energy will be reversed. The last time, what was the lower energy state? The plus half was the lower energy state. This is an oppositely charged system. What's the splitting of this going to be? The delta E for this, what will that be? Just reduce that. What was it for the nucleus? It was G into beta N. And what was beta N? It was EH by 4 pi N mass per proton. It was a Bohr or the nuclear magneton, right? And what was the value for that? 10 power minus 27, roughly. 10 power minus 27 joules per Tesla. Now, if I want to do the same experiment for the electron, the equation will still be identical in some ways, but what will be different? For the electron, G, but now it must be G for the electron, like it was G for the proton, it was G for carbon 13 nucleus, it was G for a fluorine 19 nucleus, or a G for a P31 nucleus. Now it must be a G for the electron. Whatever value I get, the G value for the electron, characteristic for this species, I take that. What will be in this case? Will it be beta N or something else? It must be the Bohr magneton, which essentially is defined as not EH by 4 pi MC, mass of the proton into C. Now it is going to be mass of the electron, in which case this becomes the Bohr magneton. So the equation basically is modified. That's why I said if you know NMR, you actually know ESR. That's the reason why I thought I would do it. Because there's no big effort really required in understanding the basic concepts of ESR if you know the basic concepts of NMR. The equations are the same. I just take the characteristic G value for the electron just as I took the characteristic G value for the nucleus. The third one is the field. Same thing. Now what's the relative value of the nuclear magneton and the Bohr magneton? The nuclear magneton is 10 power minus 27. So how much different should the Bohr magneton be? The only thing that's different is the mass of the electron versus the mass of the proton. And how much different is that? About 2000 times, right? And therefore what should happen to the value of beta E? Not 10 power minus 27, like 10 power minus 24. Don't worry about the exact value, go find the exact value. But it should be about 10 power minus 24. So what does that mean really? For the same magnetic field, what's going to happen to the splitting? It's going to be much larger. Therefore, I am not going to be working in the radio frequency region. What would I be working in? I am going to be working in an electromagnetic frequency region whose energies are about 1000 times greater. So in fact, you don't work in the radio frequency region, you actually get to the microwave region, which is what? A few wave numbers. And why does it happen? It simply happens because of the fact that the beta E is about 1000 times larger than the nuclear magneton, which was the defining parameter for the equation for the NMR experiment. So based on that, you will find that the delta E in the case of ESR will fall roughly in the realm not of few hundred megahertz or many thousands of megahertz, 10,000 megahertz or thereabout. That would be your operational frequency for ESR. So how would you do the experiment now? Apply a field and see what the transition frequency is for the electron, that lower electron in the case of hydrogen, to go from one state to the other. And of course then you have an electron transition from one MS state to the other MS state, and you then basically what you have done is electron spin resonance. As I said, this is again a very different experiment from what you normally do for UV-based absorption. There you don't have to dress your system. Here you have to dress the system out by putting a field first. Split the spin into plus half and a minus half state, and then jump from one state to the other by providing the appropriate frequency of the radiation. Okay. So this ESR experiment therefore is identical to what you would do for an NMR experiment. So if you know one, you know the other. You know the equations for one, you know the equations for the other. Because it's instead of being G beta N to Bz, it's G beta E to Bz. And the N, beta N and beta E are simply the differences between the nuclear magnetron and the Bohr magnetron. In magnitude, it's about 1,000 times or 2,000 times larger for the Bohr magnetron. What about the G value for the electron? G value for the electron is roughly around 2. And unlike for the nucleus, it can actually be calculated. Let's not get into the details of how to calculate this. Let's assume that we know this is about 2. So if I know it is 2, if I know G is 2, I know the value of beta E, and let me put beta Z, let's say 2 Tesla, then I can actually calculate what the energy difference is in terms of joules or in terms of the frequency. And it turns out that you will find that this is about 2 Tesla, and beta E is of the order of 10 power minus 10 to 24, which is joules per Tesla, and G roughly around 2, you will see that delta E over H, which is mu, will be roughly of the order of 9,500 megahertz, which essentially would fall in the microwave region. So you're basically doing an experiment in the microwave region in your ESR experiments. What sort of molecule will show ESR? It must have an odd electron, so that the spin doesn't all get coupled up. So if I have a radical, for example, if I'm looking at a metal radical, will methane show ESR? No, because in methane all electrons are paired up, the singlet state, no ESR. But if I take a metal radical, and let's say I have an experiment where I can produce a metal radical, and I want to know whether the metal radical is there or not. Well, there are many experiments. One could do in ESR because metal radical will show up in an ESR. And if I get the characteristic spectrum of a radical, metal radical, then I know by experiment actually produces the metal radical in that particular mechanism. So therefore, any radical that you produce is actually well studied through an ESR experiment. ESR is essentially meant to look for radicals and to study radical chemistry. And mind you, it's quite a useful thing because to study radicals is not so easy. And here's a technique that will actually help me to study these radicals. What I will do now is we will proceed with this argument and we will see what sort of information we can actually derive about that radical by using ESR. Now let's look at the spectrum of ESR. Let's say I have a metal radical. There is one electron which is going to jump from plus half to minus half, and therefore I must get how many peaks? One peak. There is only one electron that can make the jump. So I will get this. Now unfortunately or fortunately for the ESR experiment, as opposed to the NMR experiment, you saw the NMR peaks, right? How wide were they? Extremely sharp, right? Of the order of maybe a few tenths of hertz. They're extremely sharp lines that you were getting. When will you get sharp lines? Go back to broadening that you learned. When will you get sharp lines? If my lifetime is very long. Because if lifetime is very short, then actually I suffer from natural broadening. Will I have Doppler broadening in the NMR region? No, because that's so long a wavelength or so small a frequency that the Doppler equation, which incorporates mu naught, that mu naught is so small that the Doppler broadening isn't very important either. And that's the reason why NMR signals are extremely sharp. And the only thing that determines the lifetime of these nuclei that go up, they have to come down, is the surrounding. They collide with the surroundings and give off the energy and they come down. And that is what saves the day for us. You can keep the NMR experiment running. If what went up never came down, we discussed that in the afternoon, the experiment stops after a while. Because then the population becomes equal and then there is no apparent absorption after that. In the case of electrons, the electrons are not restricted. They sort of move around. They are more mobile than the nucleus. So what happens? They visit the surrounding much more. And therefore they tend to lose their energy to the surroundings much more efficiently then the nucleus. So what does that mean? What would be the lifetime if this was the electronic transition going from a minus half to a plus half state? Will the lifetime of the plus half state in an electron be shorter or longer than the nucleus? Shorter, because this is visiting the surroundings much more readily, and therefore the decay mechanisms for the electron spin is much larger, and therefore this state will decay very rapidly. If it decays very rapidly, what happens to the peak width? Well, they're going to be quite broad. In fact, in the case of IISER, the peaks are really broad. As opposed to a few tens of hertz, here it could be many kilohertz. Which therefore means that you're talking of peaks that look like this. Give me an advantage and give me a disadvantage. The peaks look like this. Of course, the disadvantage, right? If I don't have resolution, how am I going to even distinguish between different peaks? Well, there are ways to do that, and we will see how that can be done. What's the advantage? Well, the peaks are this broad. You know, yesterday I was talking about log frequency, and I will keep the frequency sharp. If I don't keep the frequency, the peaks get broadened. My peak is already broadened. So what am I worrying about log frequency? My instrumentation is not similar. My peak is already broad. So I don't have to worry very hard about keeping the field very constant. So there's always a silver lining in everything that happens, right? This looks like a real disadvantage, but there is something of an advantage as far as the instrumentation is concerned. Whenever you have peaks like this, how do you get around that problem and make the peak look artificially sharper? Not terribly sharper, but artificially, so that you can at least pick the peak maximum. If I ask you to pick the peak maximum over here, it's very hard. You know, where will you keep your cursor? Here, I don't know. If you did it, you would keep it here, somebody else would keep it here, and therefore you have a problem. Whenever you have a problem like this, you take recourse to very simple mathematics. Plot the derivative spectrum of this. If you plot the derivative spectrum of this, what will happen? The derivative changes. At some point it's gone from positive to negative, right? It will look like this. Then you say, okay, zero crossing of this is what I'm going to take as my peak. In other words, whenever you have broad spectra like this, people always get around that problem by actually plotting a derivative spectrum. ESR spectra, therefore, are always plotted as derivative spectra. NMR spectra are plotted as is. What you see is what you get. In ESR, you get the spectrum pretty broad, you plot the derivative, and then see where the slope actually changes. And you're going to say that's my point of inflection. That's where I'm going to be calling this as my frequency of transition. So this is what basically you do. So if any ESR spectra will look like something like this. And this actually means there are 4 peaks in there. But if I didn't plot the derivative but I just plotted the peak itself, it will do something like some wavy spectra. And very hard for you to actually figure out what is going on. But if you plot derivative spectra, you can actually pick where the slope changes, and which is an indicator of which can be taken as an identifier for the peak position. So, first, everything to begin with looked absolutely identical to NMR. Put a field, put a magnetic field, get the transition going, and therefore you have this problem. The experiment worked out. But when you actually measure the spectra, you'll find that first, they are not in the radio frequency region, they are in the microwave region. That's one difference. Go back and plot the spectrum, they are not sharp anymore. They are pretty broad. They are broad for the simple reason that the relaxation mechanism is very efficient for the electron, which therefore decreases its lifetime. And when you decrease the lifetime, you actually increase the peak width. That's your Heisenberg uncertainty principle, which we spoke of earlier. Because of which peaks are broad. If peaks are broad, how do I get around the problem? Well, I'll plot derivative spectra and get around that problem. Therefore, ESR spectra are always plotted as derivative spectra. Okay? So you see that all you have to do here is to find out where it is different from NMR. Otherwise, everything else is going to be very similar to NMR. And the next concept I'm going to talk to you about is also going to be very similar to NMR. And that is the problem. I need decoupled system. Okay, if I have a metal radical, let's go back to that. expect this electron just to sit somewhere. It's sort of moving around in the molecule. Because why is it moving around? How do you know it is doing that? Well, we know it's doing that by simply taking the molecular orbital diagram or working on the shapes of the molecular orbital, and you will find that the molecular orbital is actually smeared out over the entire molecule. If an electron sitting in that orbital actually visits this hydrogen a little while later, therefore you can actually assume this electron is actually moving around and seeing all the hydrogens. As opposed to nuclei, which really, can't get very close to each other. Because there is a distance beyond which they can't approach. You call that as covalent radii, ionic radii, van der Waals radii. Today people talk about hydrogen bond radii and so on. But there's a radii, which means that you don't cross the border. Nuclei have to stay away from each other. So which means any coupling that we talked about has to only occur not by the nuclei actually talking to the other nuclei. We saw it actually has to occur through the electrons. And it is the through bond electron interaction that was essentially responsible for the nuclei coupling. And we said if it's a 3-bond coupling, then it is okay. 2-bond coupling is stronger. 1-bond coupling is even stronger. But beyond 3, we don't even worry about it. And I think I forgot to tell you that this is actually given by a term J, which is the coupling constant. Tells you how much the splitting is. And they will give you AB, meaning atom A and atom B. For example, this is HA and this is HB. Then when I say JAB, I am talking about the coupling of HA proton, JHB proton. And you'll always find, this is trivial. I mean, this, even without my teaching you, you will realize what it is. But you'll always find when they write this, they put a number in front of it, 3. And that number essentially tells you the number of bonds that